Our talk is about DNAssim, which is basically a full system simulator for the DNA data storage. The outline of the talk will be why we need a new storage media, what is basically the DNA storage. Let me say from an information theory point of view, not a biological point of view. I'm a storage girl, so I use from an information theory point of view here. What are the error sources here? Because basically the channel we are dealing with is much, much more different in comparison with the standard channel, standard storage channel. Here we have a different metric, which is a huge difference. We do not have the Hamming distance anymore. We use the edit distance, so we will understand what it is and what are the new challenges when dealing with this new metric. Why we see the need for a simulator, so why at DNAalgo we decided to develop DNAssim. The double S stands for DNA storage, storage simulator. What do we mean here about encoding and decoding? It's not just in the standard media where basically it's the error correction code. Here we will see that there are a lot of different steps, which involves, of course, also the error correction code, but also, as has been already mentioned in the talk before me, the mapping, the indexing, compression, and these all kind of things. We will see how we need to accelerate, since we have a simulator, of course. When we use a simulator, we always deal with speed. So we would like to accelerate the simulation through software and hardware co-simulation, and then the conclusion. So why we're searching for a new storage media? Basically, today, more and more applications are data hungry. Every day, if we think about automotive, we're producing tons of data that needs to be stored for a long time. Maybe never accessed, but at least they need to be stored. So every day we hear about new data centers that popping up around the globe. But of course, it's not possible to cover all the globe with data centers. There are also some issues regarding power, space, refrigeration, and all these kind of things. So what are the benefits of DNA as a media? Basically, there are three main benefits. The first one is the longevity. DNA has an incredible retention. Here, this is the picture of a mammoth, because, of course, we were able to sequence, to read the mammoth DNA. So it's something that we can store basically forever. It is green, because it doesn't need a lot of power. We don't just a refrigerator or a capsule, but it can be stored in a test tube. We don't need too much environment in order to keep our data stored in a DNA. And a capacity. Capacity is incredible. Tons of data, as already mentioned, that by Dave has been stored something like a grain of dust. So it's really incredible. But of course, nothing comes for free. So there are some main challenges from data point of view. And I think that basically there are four challenges we're dealing with. One is the same as the benefit. So we have a huge amount of data stored together. So with the Rosetta Stone project, there are some issues in booting an archive, because basically we do not have a way to address some part of the data that are stored together. There is no position, so address by position or a linear address. So how can we discriminate if we want to access a particular file from within a huge amount of data? We did some way of indexing, basically. And also, data come out without a specific order. All the data comes out together. So when we need to read back, to reconstruct our file back, we need to understand which is the correct order in order to build our file back. So basically an index way in order to rebuild our file. And then the channel. The channel is really very different from standard storage channel because it's an IDS, where IDS stands for insertion, deletion, and substitution. So the kind of errors that happens here, it's not just flipping of a bit like we are used, so let me say substitution, but we can have also insertion of some nucleotides or deletion on some nucleotides from our strand. Then, as already pointed out, when we sequence our data, we use the PCR, so polymerase chain reaction. From, let me say, a data point of view, what PCR produces is that once we have a thread that enters the process of PCR, so SWAN cycles, basically we have a random number of replicas of this strand. But this number can be a huge number. It's random, but it can also be 0. And when we have a 0, it means that in our file, some part of the data is completely lost. There is no way also to apply any correction on that because no data is available. So, as I mentioned, my talk is about an information point of view. So what we think at DNAalgo is that in order to make DNA data storage a real project, we need some sort of data manipulation. We have to deal with information theory and data analysis and algorithm in order to make really a fast and reliable access to data stored in the DNA and make a real project, so not just a proof of concept. A lot of industries are moving in that direction. So, okay, the proof of concept has been shown, but now we need really to make a product, a real product. So, what is the, let me say, the DNA data storage pipeline? So what happens in, if we want really to use DNA as a storage media? Basically, we have our digital file, which can be anything, so an MP3, a movie, a picture, a text, whatever. It is converted in binary, so we are used for that. And then from the binary file, we need to enter the process of encoding. Encoding is not just error correction, it's a number of steps, but the key point is that at the end of the encoding, we have our file converted from binary to oligonucleotides. As already pointed out, it can be a huge amount of just, let me say, ACGT letters, but it must be split in strand because it's not possible to synthesize gigabytes of files together. So we need a way to index them and so on and so forth. And then we enter the process of synthesis, so writing synthetic DNA. DNA is stored in a capsule or a test tube, or dehydrated, whatever, and then errors occur. The errors that may occur there is insertion, deletion, and substitution. Just want to underline that because it's really key in the DNA channel. Data read back, so are sequenced, and at that point, we have our strand of oligonucleotides. But the amount of data that we synthesize is not even comparable to the one that we sequence back due to the PCR process. So we really read back a huge amount of data where there are a lot of strands that are read a lot of times, but I would like to recall it, there are some strands that might not be read at all. So at this point, some information might be really lost. Data entered the process of decoding, which also in this case is composed of different steps, and converting back in binary, and then the file can be reconstructed, our original file. So this is just a toy example of how the channel, the information channel we are dealing with. here we just have 5 strands, very, very short. And when we read it back, we enter the PCR, so polymerase chain reaction. And what happens is that, for example, the first strand is read multiple times. There are some strands that are read a few times. And there might also be like the third strand that is not read at all. So at the end, that's the reason why I said before the amount of data that is sequenced is not even comparable to the one that is sequenced. Then on each strand, errors can occur. So errors can be substitution, which are depicted in yellow, where it should be an A, it happens to be a G. It can be an insertion. So here, a C depicted in orange went in between the T and C. So at that point, also the length of the strand change because it may increase. So it's not fixed. And it can also happen a substitution. So here in light orange, where a nucleotide is lost. And in that case, the length of the strand of that particular strand is decreased. So when
Can you instruct PCR on how many copies of a strand to produce?
Okay, in the simulator, yes. But from a biology point of view,
It's out in the wild in real life. PCR is not deterministic. You're
Yeah.
getting 0 or
Yeah.
1
Yeah.
greater.
yeah, yeah, yeah.
But for each cycle, you can control how many replicates you get.
No,
No, okay.
I didn't get space for
So when we want to understand, basically a metric is fundamental when we are dealing with an information channel. So when we want to understand how many errors occurred or how far we are from the original strand that has been synthesized, we need a metric. And what is the metric that we used here? It's what we call edit distance. So the edit distance is quite easy to understand, but it's not easy at all to compute. So supposed to have these 2 strands, so we need to understand basically how many steps, including insertion, deletion, and substitution, we need to perform in order to go from one strand to the other one. So in this case, we see that a C has been deleted, so first step. Then an A has been replaced by a G, so second step. And third one, a T has been inserted, third step. So the edit distance is 3. As I said, it's quite easy to understand, but in order to compute it, basically it's based with a formula, which is a recursive formula. And this is why it's very hard to compute in comparison to standard distance in the information channel, in the storage, which is basically the mean distance, so it's much easier. Basically, it is used an algorithm that comes from dynamic programming. This algorithm is used when we want to understand which is the edit distance between 2 strings. But of course, we may think that an oligo strand is basically 1 string, where the alphabet is just composed by a CGT. So that's the reason why we can apply this kind of distance here. Suppose that we have 2 strings or do not have the same length, because of course we need to take into account that insertion may happen, deletion may happen. So maybe also the length of the 2 strands is not the same. We need to build a matrix of size n+1 times n+1, and we need to fill up this matrix. I will describe it with an example, an algorithm which is called Wagner-Fisher algorithm. So suppose that we want to compute the edit distance between two strings, which is Paolo, and the Paolo exclamation, where the first P is a capital letter. How do we compute it? So basically, we build the matrix. We initialize the rows of the matrix and the first rows of the matrix and the first column in an increasing order. And we need to fill up all the cells of the matrix. And the exact result, so the edit distance between these two strings, is in the last cells, so the yellow one. So if we go on with our example, how do we fill up all the cells of our matrix? Of course, it's made using a formula, where we need to compare each character of one string with each character of the other string, and that's the reason why it's hard also to compute it. But, so when we compare, basically the first step is we need to compute the penalty. So we compare the first char of one string and then the other char of the other string, and if they're the same, no penalty has been found. If they're not the same, we give a penalty of 1. Then each cell is computed by taking the minimum value between 3 values. Why there are 3? Because basically the first one, where there is the penalty, it's like saying that it takes into account that a substitution has happened. The second one and the third one would like to take into account that maybe an insertion has occurred or a deletion has occurred. So that's the reason why we need to compute the minimum up to among the 3 formula. And if we look at the index of these 3 different values, we see that the value of this cell need to take into account the value in the diagonal, which is the one that basically takes into account a possible substitution, the value just on the top, and the value just on the left-hand side. So that's what make the formula, let me say, hard to compute, because we have 3 dependencies. So the second cell will depend also on the first one, and this is why the formula is recursive. So suppose that now we want to fill up the blue cell. So first of all, we need to understand which is the penalty. So we compare the first char, P, with the other char, which is P, but with capital letter. In this case, we have a penalty of 1, because it's not the same char. So the first formula will be 0, which is the value on the diagonal, plus the penalty, plus 1. So the minimum between 0 plus 1. Then we will take the value on the upper part, which is 1, and add 1, 2. The value on the left-hand side, which is 1, plus 1 again. So that value in that cell will be the minimum among 1, 2, and 2, which is 1. What happens with the second one? With the second one, we have to compare A with P with capital letter. We still have a penalty because the chart is not the same. So the value in the blue cell now will be the 1 in the diagonal, so 1 plus the penalty, which is 2. The value on the top, 2 plus 1, which is 3. And the value we just have computed, which is 1 plus 1, which is 2. So the value on the blue cell will be 2. And we go on so on and so forth, filling all our table. Here we just have another example. Well, at least we just have no penalty. So we compare A with A, no penalty, because it's the same character, also the same case. So the penalty is just 0. We need to take into account the value on the diagonal, which is 1, plus 0. The value on the top, which is 2 plus 1, which is 3. And then the value on the left-hand side, 2 plus 1, which is 3. So that's why the red cell in this case is 1. Here, the example is quite easy. The strings are very short, but we need to think that our oligo strand, it's not so long, but it may be hundreds of nucleotides. So the matrix is very full. And we need to compute every time when we want to understand how many errors, what happens in the channel. So it really changed the channel we are dealing with. In any case, now we fill all up our metrics in this case, and at the end, in the yellow table, finally we had the edit distance between Paolo and Paolo exclamation with capital letter, which is 2.
What is the algorithmic efficiency that you get out of this compared to other approaches? Is it multiplicative versus exponential or?
Exponential. So what happens furthermore in this channel? Okay, we say the channel is very different. We're dealing with a metric which is very different. But then, again, the errors are not unique because the path that we can use in order to start from one strand and go in another strand, it's not unique. And then the errors are not additive, let me say. So for example, if we understand that we have a channel where we have, for example, 5% of substitution and 5% of deletion, we cannot say that the overall error is 10%. It's not true, because sometimes the errors cancel each other. So this is another complexity we are adding to the channel. Now, I just want to explain these two bullets with some examples. So why I say that the example, the IDS channel is not additive? Okay, suppose that this is what we want to synthesize, so T, A, and G. And this is what happened. So during the storing of our data in DNA, at some point, one A has been deleted, but then, later on, one A has been added. So what we get when we sequence it back, so when we read, is basically that we wanted to write T-A-A-A-G, and we read T-A-A-A-G, and we may conclude that no error has occurred, basically because two errors cancel each other. Here we have another example. In this case, we had two errors. So this is what the events that are basically generated. We had a deletion of a G, and then we had an insertion of a C. But as you can see, the length of the strand didn't change. And what happens from reading back the data is that we wanted to write T-A-C-G-T, and basically we read T-A-C-C-T. So the edit distance between these two strings is just 1. So we may conclude that one substitution has occurred, even if the real event that happened in that channel was an insertion or a substitution. So not only the errors can cancel each other, but the path in order to reach from one strand to another may be different and may involve different kind of error. In reality, we didn't have substitution, but at the end, we just had substitution, which is a different kind of errors. Here we have another example where basically 3 errors occurred, a deletion here of a G, an insertion of a T, and a substitution. But at the end, the edit distance between the two strings is just 2. So the minimum path from starting from one strand and reaching the other strand is just 2. So we may conclude that just 2 errors occurred, even if there were 3. And not only they involve different kind of errors, but may also involve different nucleotides in the strand. So at the end, we may conclude that maybe there will be an error on some place where really there were no error, but a deletion just happened before the nucleotides before, and that's the reason why everything is mixed up. Also in this case, we had 3 substitutions. This is just what I wanted to point out. We have 3 substitutions of A, G, and C, but at the end, it has been explained with the minimum path. Yes?
Are there cases where it's important to understand what type of error it was, or is the primary goal just to understand what the error-corrected data is?
That's a good question. So on one side, when we want to characterize the channel, so to build the algorithm over that channel, it is important to understand what really happened. This is what you want to, let me say, take care of. And in particular, if you want to model the channel, as I will explain later on with a simulator, we want to model channel or real data, so we want to understand the real model that they are. From the decoding point of view, it's true that it doesn't matter what really happened. At the end, what is really important is that you are able to recover your data. But this helps also if you want, for example, to put some probability of errors and make a channel very noisy. You don't want that all the channels delete each other, because otherwise you think to have a strong channel, which is not. Right. Okay, and this is one last example. But I just want to make it also, maybe it's boring to see all these examples, but just want to underline this kind of example, because in this case, what happens and what we may interpret at the end as exactly the same edit distance. So in this case, the edit distance between these 2 strings where we had a deletion and an insertion is 2. But it may also be explained with 2 substitutions. So also in this case, the path, at the end, the distance is the same, but the interpretation of the path that we need to follow, starting from one strand and going to another, may be different. So when we want to deal with let me say, hard channel with a different metric and a different error mechanism, why we want to build a simulator on that channel? Basically, we say that, I said before that the encoding and decoding algorithm is not just one algorithm, but it's a composition of different algorithms. But basically, they're deterministic because they can be described by equation, right? But errors in this channel, but in all the channels, but specifically in this channel, they are not deterministic by definition. So on the other side, we have errors that have a statistical behavior inside. But if we want to find out the best algorithm on a specific noise channel, basically, we need to model that noise channel and try to understand what is the best combination of encoding and decoding strategies on that specific channel. And that's the reason why we decided to build a simulator, because we want to model the statistical behavior of the noise and then try different combination, different parameters of the possible encoding and decoding strategy in order to be able to find out the impact of our strategy on that specific model. So this is basically a block diagram flow of our simulator, DNAssim. And here, I just want to show that the number of steps involved in the encoding and decoding is much more higher than standard error correction, right? So we have our binary file. We have, of course, the error correction. Data must be reliable, so there is an outer code. Then we need to map into nucleotides. So we also have a mapping. and can be different strategy in order to map our data in nucleotides. As we already mentioned, we need to split our file composed by ACGT and in strand, and at that point we need to index them, otherwise it's not possible to build back our file. And then we have the mechanism of primer attachment, but basically from the information point of view, just to emulate the biological behavior. At that point, we have our number of strands that have written, right? We enter into the noisy channel, which is a model of the channel that I just described, so a combination of PCR plus IDS channel, insertion, deletion, and substitution. And what we get here, it's a huge number of strands due to PCR replica. So at the end, we have a huge amount of data here, which is strand replicated a random number of times, basically. Once we have all this amount of data, we remove the primer. And then we need to understand how many replicas are more likely to be for the same strand. So we apply a clustering algorithm. So we're now trying to find out how many different sets, group of the same strand has been replicated over due to PCR. Then from each cluster, we try to find out which is the strand that has been most likely synthesized. And this is done through trace reconstruction. And here with trace reconstruction, of course, it's where we need to deal, for example, with the IDS errors or strands that are with different lengths because of insertion or deletion and this kind of thing. At that point, we map it back to binary, and finally we can apply our error correction code. Noise model in our simulator. Yes, go ahead.
Sorry.
No.
One, I guess, macro question. Who's your primary user base for this technology? Is it companies that produce sequencing and synthesis technologies? Is it codec vendors? Who's the primary user for DNAssim?
I won't say a codec vendor. I will say someone who needs algorithm. Someone who needs algorithm. So that needs to understand which is the best combination of different algorithms in order to make it reliable. Welcome. So in our simulator, that's the question that you had before. Of course, we can tune the multiplicity of PCR. So the number of replicas is tunable. But the key point is it's also that we need also to have a zero replica because it's quite a huge error because at that point the errors are the strand is lost. So it's something that we need to have in the simulator, right? And then after, let me say, it's quite exactly what I described in the toy example. We apply a tunable number of replica on each strand, and then on each strand we apply a probability of having insertion, deletion, and substitution. So it's exactly like the toy examples. This is how we model the noise in the simulator. Our simulator is managed by a graphical user interface, and we have a lot of parameters there. In fact, the primary use of the simulator is in order to make something like a design space exploration over all the possible combination of algorithms on a specific noise model. So we can add different algorithms, we can add parameters to that algorithm. And then when the simulation is complete, we have a number of graphs and text in order to understand what happened during the simulation and understand which is the best, let me say, synergy between all the algorithms on that specific noise model. This is an example. Just want to go in detail with this example because I think it's useful to understand why we think that the simulator it's needed in this environment, this new environment. So basically, suppose that we want to have two tests, test 1 and test 2. On these two tests, basically, we apply some different strategy. So, for example, with test 1, we use an outer code, let's call it A, while we use B on test 2. And we can also use different, let me say, tricks on the code, which are, like, let me say, a library. For example, AC, we apply AC on test 1, while we apply BC on test 2. Then we use the same mapping, which I call here natural. We can use randomizer, which is the same. We use the same mechanism in order to make indexing. But for example, we use a different strategy, different algorithm to make cluster. So in one case in A, in other cases D. And the same trace reconstruction. So at the end, basically, we want to have exactly the same noise model and understand which is the impact of using the outer code and different tricks on the code and a different cluster algorithm on that specific noise model. So noise model is exactly the same. So what we used here for PCR multiplicity and the probability of insertion, deletion, and substitution in the same. And what happened? Okay, we have a number of information about the noise. So, for example, the percentage of GC, the number of initial strands. This is just an example. So suppose that at the beginning we just had 20 strands. And then we have a number of sequence strands, so 450. Of course, the information is the same because the noise is the same. Then we want to understand what happened at different steps of the decoding algorithm. This is key because if you want to figure out the impact of different algorithms on our chain, we need to be able to analyze the result at different steps of the algorithm. So on the upper part, we had the result, the comparison of these two tests just after the cluster algorithm. So basically, we have the cluster ID, so let me say how many clusters we were able to find, and the size of that. So when we see 0, it's because in that case, we were not even able to find out any strand belonging to that particular cluster. So in this case, for example, for the ID 20, we just have 0 for test 1 and 0 for test 2. So maybe that strand has really been lost in the PCR process. But for example, here in the ID 10, this is not the case because the cluster strategist number 1 found out just one strand, but the other one was not able to find out any strand. And this is because maybe that strategy used for cluster B was not as good. So when we computed the edit distance, basically that strand falls in another cluster. And that's the reason why I have some little discrepancy between the two. This is because we use a different algorithm. So maybe the size of the cluster may not be the same. Then we have the errors just before entering the decoding of the error correction code. These spikes are due to where we had an erasure, so a strand that is completely lost. And that's the reason why we just have one spike, which is behind here because it's in blue for the test number 1, and 2 spikes for the test number 2. And we see that there are some slightly differences in the number of errors, and this is due, of course, to the outer code, to the cluster, of course, and also to the tricks that we apply on the code. But at least we are able to compare at different steps. And then we had the results at the end. At the end, what happened? Our simulator finished in one way with success, in another was not able to recover all the strands. So with test 1, there were one missing strand. We had a higher number of errors before the decoding, and at the end, the strand had been completely lost. So we were not able to recover that. While with test 2, we had two missing strands, maybe because the clustering algorithm that we used was not as good. But other algorithms that we used together with the clustering, for example, the outer code or the tricks on the code, were so good that we were able to have a fewer number of errors before the decoder. But most important thing, we were able to recover all our strands. So that's the reason why I just want to stress that we need to compare the result at different levels. Because if we just stop here, we will conclude that the strategy used with test 1 is much better, but it's not the case. Okay.
Thank you. I have the last. Can you hear me? Okay, you see, this is what is going to happen in the DNA storage looking forward, right? So at DNA, my name is Rino Micheloni. I run the engineering team. So we have two teams, mathematicians and engineers. And they keep inventing new algorithms all the time, and we have the last 5 minutes to execute, right? So this is the situation. Okay, here I just have a few slides, no more algorithms, don't worry about that. So the key point, and I want to go back to your question before, when you think about the DNA pipeline, and by now it should be clear, right, that it's a pretty complex pipeline. You have many stages, and you can have different implementation at each stage, and for each implementation, you have many parameters to tweak. So the design space is actually pretty big. And so when we implemented the simulator the first time, we were pretty excited, right? Like implementation of the full pipeline. And then we started running simulations, and it was like, yeah, but this is gonna take forever, right? I mean, if you're already close to the final solution, that's fine. Maybe you can take a week. But if the goal is to do a full design space exploration, then the simulation time has to be short or short enough. So, and then that's why we decided, okay, a pure software implementation is not gonna work. If we wanna build a tool that can enable like the big guys to develop a full DNA storage solution. And we decided to go an FPGA acceleration because of course ASICs DNA storage ready are not there yet, which is good for us, of course. And here you see on the left-hand side what Alessia has already shown as the high-level picture of our simulator, and then which is written in Python. And then we have a PCI Express card with an FPGA on board. And you know, the example that I brought here today is exactly about the edit distance calculation. So all the kind of table the whole table that Alessia just explained. So if you start from the left-hand side here, we have the host domain, which is our, could be a workstation or laptop, whatever. And then we decided to go for a PCIe interface because of the speed. And then internally, we have a crossbar, the AXIC crossbar. And then we have block ramps here where we put the strings to compare. So DNAssim T stands for source and target. And the orange block is the block that does the calculation that Alessia just described. So when you go to for a hardware acceleration, you have two problems, right? One is the communication to the board itself. You need to make sure that it's not taking longer, right? That the calculation done by using a CPU. And the second thing is that if you have an FPGA, of course, you can parallelize the calculation. And depending on the card that you have chosen and the resources you have, then you can, of course, change the performances. So the first goal, what I'm showing here today, because, yeah, so please.
Parallelize the calculation for recognition. It looked like it was very sequential in each computation as dependent on the paths.
Yeah, but of course you can compare multiple strings at the same time.
Got it. So it's not parallelism within the confines of determining the end
No.
distance between a pair of strings, but running multiple concurrent operations
Exactly.
for separate sets.
Yeah,
Okay.
exactly. Yeah, so I think the first point, as I said, was for us to understand if, because it's not a given, right, that it can accelerate by using hardware, because you have the communication with the, with the software infrastructure. So here we decided for a parallelism of 32 here. And actually we already got pretty high occupation of the block RAMs here. You see 87.4%. And then we looked at our software driver, because that's the other piece, right? The latency and the bandwidth you have when you are communicating with the FPGA. So our simulator, left-hand side, is in Python. And then we do the data conversion in C, and then we push the data to the FPGA by using essentially a DMA engine. This is the FPGA. So as you can tell, pretty busy, right? So you see here like different colors. So the computational blocks is where you compute the edit distance, the 32 blocks I was talking about before. So that's the red part. And green is the PCI interface. And then the magenta one, so the DMA engine is pretty small, actually. And blue is the VRAM. It's not like a single block, it's spread out to optimize the area occupation. And then the other thing that is consuming a lot of space is that it's good to have parallelism, but then basically you have to distribute, right, the calculation among all those blocks, and actually it takes quite a bit of space. This is like what we have today. So you should look at a graph here. So you have on the x-axis the DNA strand length from 120 to 254. So the red line is software in terms of thousands of edits per second. It's not as flat it looks, right, because of here it looks flat because of the scale. But numbers are actually pretty small. And that's why it takes a long time to complete. While if you implement the right software driver and you do parallel computation on the FPGA, you can really boost the performances here. You see for 120 DNA strand length, we got slightly above 700K edits per second. And yeah, so right now we're working on the second generation. I think we wanted first to prove the concept, have a proof of concept that acceleration can really work and make a difference. And of course, by having an FPGA or multiple FPGAs, and that's the reason for going for PCIe, because you can have a peer-peer communication between the cards, you can accelerate different functions. So the system actually, was pretty simple. So we have a workstation, and then you just see the motherboard of the workstation at the bottom, and then the FPGA card we use is just plugged into the motherboard. And then the GUI that Alessia was talking about is what you see here on the screen. Okay, so I'm just going to go for the conclusion then. So I think here we wanted to highlight a couple of things as we have, long history in Flash. The error model is totally different, this is something we need to take care of, right, and model it properly, because today we see that for synthesis and sequencing, let's say different people have different opinions. So we need to be, flexible at this point. Being able to do a full design exploration, so having a platform that in a reasonable time can give you a feedback is the only way we see at this point for choosing the best set of encoding and decoding algorithms for each specific couple of synthesis and sequencing technologies. And to make this happen, the only way we found was to accelerate by using hardware, FPGA in this case. So we might also foresee that in the future, on big equipments, people will develop ASICs, right? Which of course will have higher performances and lower power consumption, but this is kind of something for the future, I would say. Please.
So do you sell just the software, or the software plus the hardware, or is it a package system that the customer would purchase?
Well, both. Yeah, depending on what they're looking for. And I think the biggest challenge here is that this is strongly coupled with the synthesis and sequencing technology people have. So that's where actually we do most of our job, right? Yeah.
So we've got 5 minutes until the next talk. So we could do a few. We're using up our break between the talks, but that's fine. So we can take questions for 5 minutes.
Yeah. Sure. Okay. Okay. Thank you, guys.
Yeah.
Thank you.